In this video, I will talk about time series ARIMA models in SAS. Before you watch it, please make sure that you have watched my other two videos called Time Series ARIMA Models and Time Series ARIMA Models Example. So I have opened up the SAS program and I have already executed the program, and here are the results. And if you would like to download the program, the data, and follow along, go to my website. The link is below the video. So we start by importing the data, and the data is called time series underscore PPI. So it's a producer price index, and to reverse engineer and use this code for your problem, you just need to change which kind of data you're using here. Next, we'll be creating a few variables. If PPI is the variable of interest, DIF is what creates a difference in the variable. So this period minus the previous. So I will call this D of PPI. You can create a lagged variable by using the lag operator, and I'll call this the LPPI. And you can create the lag of the difference, and that would be LDPPI, I'll call that. So try to create as many of these variables in your own data: the difference, the lag, and the lag of the difference. Next, I am going to use some statements here to call the variables PPI, which is the original variable, a Y list. D of PPI, which is the difference variable, I'll call that DY list. T, what's in the data set, I will call this time. And I had the lag, the Y variable. I have a trend variable in my data set, which will remain as trend. And I have an X list for a few variables that I will use in regressions later on. So try to generate as many of these variables as possible for your data, and then the rest of the program, except for right here when we have the Dickey-Fuller test, should work with just about any data set once you've declared them, your variables. So the first thing to do is calculate some means of the data of the Y and the difference to Y and time. And here we have 169 observations, the means, and standard deviation, minimum and maximum. Next thing we can do is we can plot the data using proc gplot and calling the data set. And here we can plot the Y variable, our original variable, which is the PPI, this one, against time. Or we can plot the difference variable against time. So this is the original variable that we have here. And look at how it's increasing. It just does not seem stationary to me. The next thing, we can plot actually the difference variable. And here it looks a little bit more horizontal. It doesn't look like the mean is changing, but the variance unfortunately is changing, which I'm not going to do anything about this in this example. But yeah, you have to take care of this if your problem includes non-constant variance over time. So the next thing to do is some ARIMA identification, and we will use the proc ARIMA. You're calling the data. We're using identify variable. You put here your variable, and then stationarity and ADF. And so these are the results that we have here. So a few things to look at here is some of the values that I have actually put in the table in the handout called Time Series ARIMA Models Example. So we are looking at this value here, minus 0.26, that tau here. That's the test statistic for a Dickey-Fuller test when you have a mean, and the p-value for that is 0.93. And here we are concluding that if we look at the original variable, we basically that original variable is non-stationary. So we can put a trend down here and look again at this tau, which is minus 0.79. Again, the p-value is 0.96. So basically, again, we are rejecting the stationarity. So we have non-stationary, well, we cannot reject the non-stationary null hypothesis is the correct way to say it. So this is what this p-value is showing. Now, it's a bit hard to see what these taus and p-values are for here. So in the next step, what I'm going to do is I will actually show you the regression that the Dickey-Fuller is actually estimating. And you can do a proc regression and then you have model. And if you look at the first video that I have, time series ARIMA models, we discussed that Dickey-Fuller test is if you have the difference dependent variable on the left hand side and the lagged one on the right hand side. So this is delta yt and this is yt minus 1. And here we have delta yt minus 1, and that's a trend, just a simple time trend. So these are the regressions that are being estimated. So for the first regression, here's the result right here, where you have the lagged variable is right here. That's the coefficient on it. And this is that t-value, is that tau that got reported on that table that I showed you before. So here we're testing, is this parameter significantly different than 0? It's not significantly different than 0, and therefore we have non-stationarity. Now we can look at the next one, the next regression, and this regression includes a trend. So again, difference delta of yt is the dependent variable here, and the lagged basically the lagged variable yt minus 1 is an independent variable plus a trend. And so here this is the coefficient, and that's the t-value, that tau that got reported in the table. And here we would say again that this coefficient is not significantly different from 0, therefore we have non-stationarity. It's basically not a good thing, since we have to difference the data to see then if the difference is stationary. Okay, so another thing that we probably ought to do is look at the ACF and PACF graphs, and this was done in the previous step, so I'm going to back up a little bit to show you these. And they are right here. This is the original variable that we have, and this is the ACF. You see it says ACF here, and these are the different lags of the variables, and you see a very slow decaying function, which indicates that the process is not stationary. And here we have a very strong first lag. So again, all the indicators, the Dickey-Fuller test, these test statistic, everything indicates that the original variable is not stationary. Look at how it's increasing. So we would need to difference the data. So in the next one, that's what we're doing. Okay, so this is the new ARIMA model. There's so many results in here. Okay, so this is an ARIMA model now. The ARIMA for the difference variable, and look, everything else is the same as what we have up here. Notice the only difference here is that I put a 1. So this means the variable now is integrated of order 1. So instead of like looking at the variable itself, we're looking at the difference variable. So now we need to look at these here to show to see if the variable is stationary or not. So this tau right here, that is actually the test statistic that I've reported in the table in the example handout that I've given you. And so here now we have a test statistic with a very, very small p-value, which means we're rejecting the null. We have the alternative hypothesis, which means that the process is stationary. So now once we difference the series, and so here's the different series now that looks stationary. So we can also look at the ACF function. You see it's kind of tailing off, but not like smooth like it was before. It's like that. And on the PACF we have one very significant lag on the first lag, and then nothing else seems to be significant. So these two, the ACF and PACF, if you compare that to the theoretical, shows that you do have probably an AR1 process going on. So this is what we'll try to estimate. Okay, so now let's start and estimate different ARIMA models. So when we say ARIMA, the first number here is P, the number of autoregressive terms. The next one is D, how many times the dependent variable is integrated. And this one is Q, the number of moving average terms. So 100 is basically an AR1 process. And here we have everything the same, except we're saying P equals 1. And that's how SAS knows that we are having an AR1 process. Okay, so if we look at the results, these are the coefficients that I'm again reporting in the handout. So one thing we're noticing here is the coefficient on yt minus 1 is very close to 1, and it's very significant. So this again tells you that's a non-stationary process. Okay, then the next one we can do ARIMA 200, and you just change here P equals 2. Okay, so let's look at P equals 2. There's a lot of output here. So here's a P equals 2. So again, now we have two lags. So this is a yt minus 1 and this is a yt minus 2. That's the coefficients on that. So again, we have coefficients that are significant on these two. Then we can estimate a moving average 1. Okay, so looking at the moving average 1. These are the results, and we have significance on the MA1 process here. And then the final one to do is an ARIMA 1-1, which is reported right here. So we have an MA and AR1, but look again, this coefficient is so close to 1. Because of the non-stationarity. So anyway, we really shouldn't be estimating ARIMA models for the non-differenced variable here, because we know it's non-stationary. I just wanted to show you how to estimate these models for the original variable if your problem that you're doing requires those variables. Now, one thing also to note here is that SAS usually gives opposite signs right here of the MA component that says theta or R. So you need to be careful when you write the equations in your paper, that when you have the lagged moving average terms, these are the terms on the error term, these are the error term, the lagged error terms, that you have a minus sign in front of the coefficient so that you get that coefficient right, or you just reverse only the moving average coefficients. Okay, so the next model to estimate, we're going to start with the ARIMA 110, and 1 means integrated of order 1. So what makes it that is that you see here you have D of Y list. So this D variable, you see how it's different? There's no D in here. So, and we're still doing a 1 autoregressive term. So the results are right here. Okay, so here I think I scrolled down too much. So here are the results. Okay, so we have the autoregressive term here is 0.55 and it's significant. Okay, so this is a smaller value than 1, and we know that the difference series is stationary, so this is a very good result that we have here. By the way, I'm also in the handout, I'm also reporting the AIC and SBC, which is the same thing as I call the BIC, the Bayesian Information Criteria. And so these values are also reported in the table, and they're just slightly different between the three software that I'm showing you here. Okay, so the next model that we're considering is the ARIMA 011, and this is the result that we stumbled upon right here. So we have a moving average of minus 0.48. So again, in my table I put it as a plus sign here, and we have that one significant. But we actually know, because we're looking at the ACF and PACF, that we need to use an AR1 model because of the tailing off here and the strong lag on the first one. So let's estimate the ARIMA 111. And that's that one. So we have, again, very strong first autoregressive term and a moving average term as well. So I actually like this model a lot. We have significance on these. Well, this one is marginally significant, the moving average component. But the AIC and BIC criteria are good. So this is actually my preferred model as of now. And I have two more models here, the 113 and 213. And so basically I'm putting 3 terms on the MA component and just increasing this to two legs on the AR process. So again, we're looking at these results here. We have 3 MA terms, but they are not very significant, unfortunately. So I don't know if that's a very good model. And then we have AR still very significant. And so here's the final model that we're estimating with 2 AR terms, which are both significant, and then we have 3 MA terms, and we have this one is significant. See, this is the t value, and this one is significant. The one in the middle is not. And so I also like this model a lot based on 2 criteria. First of all, we have good significance of the coefficients. That's important. But we also have still relatively low AIC and BIC criteria here. So for me, it's a toss-up between using this model, the ARIMA 213 and 111 that we decided before. But definitely has to be an integrated variable of order 1. It's not the original variable. Okay, so another thing that I can show you here is how to incorporate independent variables, and I define these in my X list above. So you need to put this in a proc ARIMA, you need to put cross correlation and put here the X list and put the input as an X list as well. And you can put here again the AR and MA components. So pretty much everything else is the same. So here are the results. Okay, here are the results. Okay, and this is the variable, and you see like I had the CPI as independent variable and the GDP as independent variable, And you can see these are the estimates. One of them is actually not significant. And you can again see the AR, they remain significant. This one is just marginally significant. I'm looking at this t-statistic and the p-value. And again, the MA component, that one is not significant. And again, remember to reverse the sign or do something about it, either in the equation or in the table, if you've used plus on the MA terms. Okay, so this is how to incorporate the independent variables. So the next thing that you can do is you can forecast in the future some of the values. And the way to do that is actually you estimate the model and you put here forecast lead equals 12, and this one actually is a flat forecast afterward, and this is the level of the dependent variable and just flat forecast, and this is the confidence interval. Or you can forecast the ARIMA 111 model. Everything else is the same. You include here forecast lead equals 12, and this is what we have for that one. So it's basically re-estimating the model, and you can see now this is the difference variable we have. This is the forecast, and that's the confidence interval around it. Okay, so that was a quick tutorial on how to do time series ARIMA models in SAS. Thank you for watching.